In this example, we have block P, which is initially moving to the right with some known speed, 2 feet per second, along a rough horizontal surface for which we know the coefficient of kinetic friction, mu k. There's a force F that's applied at time equal to a 0 that's shown by this function there to the right. And what we want to know is, as a result of that applied force F, what is the speed of P at t equal to 0.4 seconds. We're looking for a change here in speed versus a change in time. So I think that the linear impulse momentum equation is going to be a good approach, because that very clearly relates for us a change in speed for a change in time. Whichever approach we use, though, the first key step here is to draw an FBD. The force is acting on a block. We have the known applied force here of F. We have a normal contact force N. We have weight force, and the important friction force, which is acting on the block. Since the block is moving to the right, the friction force will oppose that, so that friction force is acting to the left. And I'm going to use X to the right and Y up. And from this FBD then, we're going to apply the linear impulse momentum equation. But the first thing I'm going to do is sum forces in Y. Sum forces in Y, as this block moves along to the right, we have the negative mg plus n. And since it remains moving along a horizontal direction, its acceleration is a 0. So what we get here is the normal contact force there is mg. Now we'll apply the impulse momentum equation in X. We've got the applied force F, positive, and the friction force with a negative because it's acting to the right. So what the impulse momentum equation says is that if we integrate the resultant force in X in time, that's equal to mass times the change in velocity for that block between 1 and 2. Okay, so what we have here then is that the integral of f dt, that's our first term, we subtract away then the integration of friction, which is mu n, and therefore that's mu mg dt. And the right hand side then again is the change in momentum. This force is a constant, so we can bring that to the outside. The integration of the applied force minus mu k mg delta t, like that, where delta t is the 0.4 seconds. So again, what we want to do is find v2. So from this equation, we can see that v2 then is equal to the initial velocity v1 to the right, plus 1 over the mass, integration of the force in time, subtract away mu g delta t. So the only thing that we need now in order to evaluate the speed at the second time of 0.4 is we need to integrate f over time. Well, what we can do is look back at our function f. The integration of f over time is nothing other than just the area under this curve. So if I break this up into two parts, one between 0 and 0.2, and then the last half between 0.2 and 0.4, we see that the area under this curve then is equal to the first between 0 and 0.2, it's a base of 0.2, height of 16. And then between point 2 and point 4, it has a base. That rectangle has a base of point 2, and the height there in that case is 8. So from this, we know that since V1 is 2 feet per second, the mass is 20 divided by 32.2, so this becomes this. We have 0.2 times 16, so that's 3.2, and 3.2.1.6, so that's a 4.8, like that. The coefficient of kinetic friction, that's 0.3. G, 32.2. Delta T is 0.4. So with that, we find the speed at 0.4 seconds in time. So what did we do? Well, it was just a matter of applying the linear impulse momentum equation in the x direction. We know that the resultant force in x, the applied force minus the friction force, the integral of that in time gives us the change in momentum. We break that resultant force into the applied force F and the friction force. And the part we need to think about here is how to find the integration of F in T. That's just the area under the curve. We got all that. We put the pieces together and we get the speed V2.